one more minute. Okay, maybe we can slowly start. I can start by introducing you. So welcome everyone to the second day of the ALA workshop. Today we have two exciting invited talks by Erke van Of and by Peng. So we'll start with Erke. And Erke is an assistant professor at the University of Amsterdam and also a member of the Amsterdam Machine Learning Lab. Erke obtained his PhD at the Technical University of Darmstadt, and more recently he was a postdoc at McGill University. Erke is interested in reinforcement learning with structured data, and that takes benefit from prior knowledge. And I believe he will tell us about this today. So thanks a lot, Erke, for accepting our invitation, and the floor is yours.
Thanks for the kind introduction. So my talk today is entitled Learning Agent Policies with Reinforcement Learning and Structure. So I'll get right into it. Oh, if I can, yeah, I can. Okay. Right. So of course, right. I guess I'm not saying.
Sorry to interrupt. We can see the color palette. I'm not sure if that was supposed on the right, so we can see the color palette. And...
Oh wait, is it not sharing the full screen? Now you can see kind of the.
Now
I see. Oh, I think I just have to remove these, and now it's fine, right?
Perfect. Yeah, perfect.
Yeah. Okay. With some issues. Right. I think I'm not saying anything new, right? That if we are developing agents, often, right, they have to make decisions, and if the agents are to do something in the physical world, like robots or autonomous vehicles, or maybe recommender agents, then there's often a real cost to exploring, right, to making mistakes. So at the very least, missed opportunities and perhaps accidents and so on. So we really want to be able to, right, learn with the least amount of data and the least amount of mistakes, let's say, possible. Of course, learning to make decisions is captured very natural, right, in the reinforcement learning framework. So, and in the reinforcement learning framework, interaction is typically modeled as a Markov decision process. So of course, an agent observes the states of the world, then picks an action. This action is fed into the environment that emits the next state and a reward, which are then again fed back to the agent who can make the next, take the next action. And of course, right, the goal for the agent policy pi is to find a policy that maximizes the cumulative reward over time. And right, I guess we often don't really think a lot about kind of maybe this framework in itself. But maybe it's good to kind of realize, right, that it's an extremely general framework. So we have very few constraints on the possible, for example, policies or value functions that we could have, and we don't assume any knowledge about the environment. So on the one hand, that's of course kind of really nice because we have something really general, something that we can use in a lot of different settings, and almost any problem you can think of, you can somehow formulate as a reinforcement learning problem. But it kind of also at the same time comes with a cost, right? Because if we want to learn something super general, then typically we need also lots and lots of data to kind of pin that down. So this is a slide from a PhD student, Elise, who likes to point out, right, that these, especially the newer reinforcement learning frameworks tend to use like massive amounts of data. So if you compare kind of the number of samples that architectures like Rainbow or Unreal were trained on, you see these are more than one order of magnitude more than, for example, the number of images in ImageNet. And ImageNet is kind of known, let's say, computer vision is a big data set, right? So you see in this graph that even MNIST or CIFAR or something like that don't even show up because, right, they have less than 1 million images. And that makes, right, hard to apply these methods to these domains that I talked about, right? Where there's kind of this real cost to obtaining all this data. Okay. And what I've become interested in is, can we make this problem somehow easier by essentially making it a bit less general, right? So if we can add some structure, so for example, restrict the search space for policies or value functions, or maybe adding some prior knowledge about the environment, we can maybe reduce this big kind of, let's say, search space, and maybe make it much more efficient to find solutions. Right. So I'm not kind of saying, okay, we should tune all our methods and our models for, like, say, super specific applications, because, right, at some point you're kind of losing a lot of the benefits that you get from adapting a learning framework in the first place, right? So you don't want to spend like lots of effort to formalize all of this prior knowledge maybe you want to feed your algorithm, or you don't want to spend a lot of time very carefully crafting some architecture for every new task you want to do. So we have to consider, okay, how much manual labor has to go kind of into designing this approach. If we are kind of making assumptions about the kind of, for example, policy or value function we need, is that a rather general assumption or something that's extremely specific for this task we're trying to learn? And also, are these restrictions, are they explicit? So do we, is it kind of transparent what we're asking of our model? Or are we kind of just adding in some hacks and we kind of don't exactly know in what way this will influence the results we're getting out? Right. So in my group, we try to find transparent and explicit ways to add structure without too much manual effort. And in this talk, I want to discuss about two specific case studies. So one line of work where we looked at restricting the class of policy or value functions using known symmetries. And another work where we experimented with adding ontological knowledge from publicly available data to provide an agent with knowledge about the world. By the way, if you have a question during the talk, clarification or something else, yeah, do feel free to ask. I can't promise that I'll notice everything that comes up in the chat, but I'll try. Or maybe Fernando can give me a signal if there's some questions in the chat. All right, so I'll dive right in with the first study. So this was about a technique we worked on called MVP homomorphic networks. This was joint work with Elise van der Pol, who was the lead author of this work. She was a PhD student with me, Frans, and Max. She's now with Microsoft Research. The other co-authors are Daniel Worrell at DeepMind and Frans Oliehoek at TU Delft and Max Welling at the University of Amsterdam Microsoft Research. And the presentation is based by an earlier presentation by Elise of our iClear paper of this year and an earlier NERLIPS paper. Right, the problem with these kind of large data sets that we need is especially bad if we have kind of this complex high-dimensional domains, right? So think about these Atari games or other situations where we have visual input, maybe also autonomous driving, for example. Because let's say, at least in the most naive analysis, right, you would say, okay, if we have these huge observation spaces or huge state spaces, we might need to learn what to do with each of these possible observations that we could see, right? And that's a huge amount of possibilities. So, right, very clearly, we need to do something a bit smarter. And one of the things that we could look at is that there are clear relationships between some states and other states, or some observations and other observations. And not every new observation requires a unique behavior. So if you take a look, for example, at the two images here on the left, it's actually a single image, but just rotated by 90 degrees, right? So you might have noticed that. So if we now teach a robot to, for example, pick up the screwdriver in the left image, and it has never seen the right image, it seems there is some, let's say, transformation, how we could take the kind of movement we had in the first image and transform it so that it also works in the second image. And for maybe a bit more abstract example, on the right, I've taken 2 screenshots from the card pool environment in Mujoko. No, sorry, in Gym, where you can imagine on the left, right? So maybe for people that don't know this particular system, this black box is a small card that can move left or right on this gray rail. And the brown pole is a pendulum that's kind of loosely attached. So it can rotate, but we can't control that rotation, or we can only control it by moving the card, and we want to avoid the pole falling over. So it's a little bit similar to if you've ever tried to balance a broomstick on the palm of your hand. And we can also imagine that if this pole is kind of falling over a little bit to the right, as in the left image, we can correct for that by moving the card to the right, kind of moving the card under it. But once we've learned that, perhaps if the pole is now falling over to the left, right, there should be a direct analog, right? So we can just flip the behavior that we already learned to also deal with this new situation. So in this kind of situation, it seems if the optimal action for, let's say, one of these input pairs is known, then the optimal action for the other, or maybe multiple other inputs, is directly predictable. So we don't need to have ever experienced that in the world. And what we try to do in this work is to use these symmetries to design less data-hungry networks. Right. So maybe first we want to kind of take a short break and kind of think about what is a symmetry in a reinforcement learning problem. And you can define that probably in different ways. And we use this definition here that was originally proposed by Ravindran and Barto 2 decades ago. We look at whether we can find a function g of s and g of a such that the following statement holds for all states and actions. So essentially what we want is that the reward is the same for the transformed state action pair, and the transition dynamics are also equal if we transform each of the state, the action, and the next state using these 2 functions. So if we can find functions gs and ga such that these hold, then these two poles, SA and G of S and G of A, are symmetric state action pairs. And in that case, we have this theoretical result that tells us, okay, the optimal policy, so the probabilities assigned to each of the actions, should also be the same for these symmetric state action pairs. Now that's quite abstract, so we can look at maybe a very simple example also from that 2003 paper. So here we have kind of a small maze, right? So the agent is to learn to get to the goal on the top right. So you can imagine maybe we've been at state A a bunch of times, and we've learned from state A, the shortest path to the goal starts out by going east, right? And then I don't think I have a mouse cursor here, but from state A, we can go to the right and eventually make it to the goal. Now, if we come to state B that maybe you've never seen before, we see that this maze is actually symmetric, right? So there's a mirror symmetry along this diagonal. So where in state A, we had to go east, now in state B, we have to go north instead. So if we transform the state by mirroring it in this diagonal, then the action should be, we have to kind of switch north and east, and we have to switch south and west. So yeah, that illustrates this perhaps this property. And what we now ask ourselves is, can we design neural networks such that they can exploit these symmetries? And to get a little bit of a taste of what that would mean, I'd like to start with looking at a convolutional neural network. So here we have we have the input here is a temporal signal. And then our convolutional network will work by just shifting the filter over the time steps, right? Right in the let's say in the middle of the image, you kind of see the features computed by the convolutional layer. You see, of course, the different feature maps that are these different, let's say, vertical vectors. And we see, for example, as this red filter moves across the signal, we kind of get the one by one the input in this frontmost column. And similarly for different filters that each kind of create their own feature map. And right, so what are the kind of the transformations that we could apply, or what are the symmetries in this kind of system, right? So you can think about that. So a kind of very natural transformation in this case is that we could translate the input signal, for example, by one time step or by any number of time steps that you like, right? So what will happen, okay, this whole signal will just move a little bit. So that means that whichever activation the filter would usually pick up in the first row, it will now just shift exactly to the second row, right? So the consequence of a 1 unit time shift in the input signal will also cause a 1 unit time shift in the output signal, right? So this is very obvious, but yeah, this helps us to look at what does it mean to be equivariant with respect to such a symmetry. So, right, in fact, we have 3 possible transformations. So we have a possible transformation on the input signal, which is just shifting the entire thing. We have a possible transformation on the output signal, which is in this case also shifting the entire thing. And we have the function f, which is actually applying the convolutional layer, right? So it's a mapping from the input to the output signal. And we can visualize this process in a more abstract way. So here on the right, so we have this kind of, let's say, upright dog, and then this rotated picture of a dog. So we can imagine, right, we can apply the convolutional layer, so the function f, we can apply it to the original image, then we come to some point in feature space. Or we can apply the function f to the rotated image, so we get to another point in feature space. Right, and now if we design a neural network, what does it mean? If we design a neural network to be equivariant to rotations, that means that if we rotate the image, so if we apply the transformation g, turning the original image into the rotated image, then there's kind of a predictable and known transformation also happening in the feature space. So essentially, no matter whether we apply first the function g and then the function f, or we first apply the function f and then apply a function g prime, which might be a different one, then we are guaranteed to end up in exactly the same point. And in case of a convolutional neural network, right, both of these functions g correspond to a shift in the signal, g and g prime, but it might not be the same for other symmetries. Right. So the question we now ask ourselves is, can we also design networks that are equivariant to other transformations, right? So kind of, find more general approaches in these convolutional layers. So convolutional neural networks are, of course, right, well known, but there's not really a, let's say, simple recipe to create layers that are equivariant to other types of transformations. So such as maybe the transformation that we just saw in the maze with this flip over the diagonal. One thing that you can do is for every transformation, try to do some clever engineering to come up with an architecture that fits that symmetry. But that's right, then kind of for every new symmetry, you have to kind of again do that work, let's say, manually. So what we did here is come up with a new data-driven approach. So to illustrate that, I kind of create an example of a symmetry. So let's start with the left of this equation, right? So here we see we want to learn a mapping from this vector x1, x2 to y. So we do that in this case with a super simple linear layer, right? So we just have these weights, W1, W2, we just take the inner product, right? So it's basically a linear regression. The twist is now that we want to enforce a certain symmetry and this is what is on the right-hand side of this equation, which is if the order of the elements of the input vector change, if we flip x1 and x2, then we like the output y to be exactly the negative of what it was before. Now, this is not very, let's say, a very intuitive symmetry, but it helps to illustrate how our method works. But you can, of course, directly relate this to what you saw, for example, in the maze. If the input state changes in a certain way, then we also want the action output, for example, to change in perhaps a certain other way, right? So then we want to flip north and east. And now the way that so what we now want to do is to find a way to optimize the neural network weights, but in a way that we always respect this the symmetry. So we always respect this relationship between what should come out when we input x1, x2, and what should come out if we input x2, x1. And how we do that is first, we kind of have a, let's say, pre-computation step. And in this pre-computation step, we first generate a whole bunch of just random weight vectors, right? So that doesn't seem like super sensible, but it helps us to find the set of weights that obey this symmetry. So we generate a bunch of random weight vectors, and of course, most of these will not obey the symmetry, right? Because they just randomly generated. And now we define a particular type of transformation that takes any of those weight vectors and changes it such that it becomes a weight vector that does respect the symmetry. So essentially, there is a transformation that brings all of these points to a subspace. And this subspace we can then identify by doing a singular value decomposition. So then we will find this linear subspace. And in this case, it's of course, a very simple subspace that's just defined by W2 has to be equal to W1, and then the above equation will hold. And that will make optimization of the weights much easier because, in the little example, we had two weights to optimize, W1 and W2. And what we see now is that we really only have one degree of freedom, right? Because if we, for example, if we know W1, then directly also we know W2, just have to flip it. The real magic here, of course, is in this transformation, right? So how do we take this weight vector and generate a this kind of weight vector respecting the symmetry? So we propose this particular projection operator, which we call the symmetrizer. It goes a little bit too deep to really go into the details of this equation, but of course we do in the paper. What I do want to go into is, okay, now the question is, of course, well, does this type of method actually work? So what we now have is a way to look at the weights of a neural network layer. In the example, it was a super small layer, but we can do that also for, of course, bigger layers and different kinds of layers. Train that layer in such a way that it respects a certain symmetry, whether it's a mirror symmetry or this kind of more contrived symmetry on the slide here. So, of course, when we can do this for one layer, we can do it also for multiple layers. And we have this nice property that if each layer is equivariant, so if each layer respects the symmetry, then the whole network will also respect the symmetry. So what that means is that, let's say we have a policy that's trained to take a certain action with a certain probability in a particular state. So let's start at the top left of this diagram. If we apply the policy to this state, we get a certain distribution over actions. The property that we now have is that if this policy is applied to a transformation of the input, in this case, a transformation is again this horizontal mirroring, then the policy applied to that transformed input is always equal to a predictable transformation of the original output, right? So there's two routes that lead into this bottom right cell. So either we can apply the policy to the new transformed state, or we can transform the policy applied to the original state, right? So if we guarantee that this is always the same, So that's really nice, because let's say if we wouldn't really know otherwise what the policy would be coming from the top right image, yeah, this network structure guarantees that we'll do the right thing as long as we know what to do in the original image. We can, of course, evaluate it experimentally. So these are two of the experiments that we did. On the left, we have again the cartpole system. In the diagram, we see the average return on the vertical axis and the number of time steps on the horizontal axis. The red lines here are different normal multi-layer perceptrons, so that do not use this symmetry. And the green line here is the equivariant is our equivariant method. And we see that both in the end find the optimal solution, but the equivariant neural network does so about twice as fast. This, of course, this cartpole system has relatively low dimensional states, right? Like I guess it's 4-dimensional. In Pong, of course, right, we have this image-based input, so that's typically right trickier from that perspective. Here in the same kind of diagram, we now have the red line is still the let's say the regular type of convolutional neural network, in this case convolutional, of course. And then we have the two gray lines that use different types of data augmentation. So in data augmentation, you just kind of take the input data that you get, but then you might kind of flip those the images that you get before training the network, so the action image pairs actually. So that's another way to handle the symmetry. But as we can see from this experiment, that's not nearly as effective as using the essentially reflecting the symmetry in the neural network rather than in the data. Yeah. So as a conclusion, if we use these this method, we just need fewer interactions with the world. Now, especially I think for this particular workshop, it might also be very interesting to look at multi-agent systems, right? So we have multi-agent systems in traffic, in video games, maybe in managing an electric power grid. Yeah, then we might want to also find controllers for that. And in this work, we only look at fully cooperative multi-agent systems. So let's say all these cars want to together make sure they get out of this traffic jam, let's say. In the particular example we look at here is a traffic light control system. So we see here we have these 4 different crossings, 1, 2, 3, 4. And at every crossing there is a traffic light that can either let the traffic through in the north-south direction, or it can let the traffic through in the east-west direction. And the goal is, of course, to make the cars wait as little as possible. Right. And we can approach these kind of multi-agent problems in 2 ways. Either we can do it in a centralized way, where there's one controller that looks at where all the cars are and then decides what all of the different traffic lights would do. That's not super scalable because, yeah, if you get more traffic lights, right, the kind of policy space just gets super large. Or we can do it in a distributed way where every traffic light has its own controller that looks at the cars in the local neighborhood and then decides on basically on what to do. But of course, it does need some information to do its task very well from what's happening in the other parts of the system, right? So they can also communicate with each other. For example, traffic light 2 could say to traffic light 1, hey, there's lots of cars coming in this direction. Maybe you want to make sure that the east-west direction is as free as possible. Now, the centralized setting is relatively straightforward because there basically we're just training a single policy, right? So there we can apply exactly what I've just said for the single agent setting. We can make sure that we have a policy that when we encounter a situation where the whole let's say world is rotated, so the cars are in different places, but right, there's some relation to where they were in the original image. That means there's just going to be also a transformation of the policy. So if the, for example, if traffic light 3 would handle these red cars in a certain way, now these same red cars are kind of located at traffic light 1, be it in a rotated configuration. So the gray bars that represented policy 3 on the left-hand side are now moved to this policy 1 on the right-hand side. So that's for the centralized setting. For the decentralized setting, it's a little bit tricky, because what we want, of course, is this kind of global transformation behavior, right? So if the whole situation were somehow flipped or rotated, we'd want our actions to correspondingly rotate. And that's what we see on the left, on the left branch of the triangle. However, if we take for every agent, we take the local observation that it has and rotate just that local observation, we don't get to the same point, right? Because essentially, if we rotate the full image, what was first in the top right now ends up in the bottom right. Whereas if we just rotate locally, it stays in the same, this patch stays in the same place. So it's not the same. So we can't directly kind of naively apply the type of networks that we used earlier to these to each agent individually. So we need to do something a little bit more complicated, and it's related to that the output of the agent is not just whether, how it sets its own traffic light, but it's also like what communication do I send to the other agents. And both should in fact transform, right? Not only kind of, let's say, the first type of output. So another way to think about that is say, okay, we want to go from the original state to the symmetric state, which is the whole picture rotated. And we can get there in a number of steps. So this, right, what's shown here is one global transformation that we cannot do if we want to have operations that only works at the individual agent level and not in a centralized manner. So we want to break this up in kind of local transformations or local decisions. And how we can do that is to first permute the observations. So the bottom left image goes to the top left goes to the top right, and so on. But then we also have to transform the edges, because the type of message that would be sent from let's say the bottom right agent to the bottom left agent, indicated by the little red lines in the original image, should now become the message sent from the bottom left agent that's already permuted, but it should be a message sent to its northern neighbor. So these edge types have to be transformed as well. And then finally, these local transformations have to be rotated, right? So if this 3-step process, and then through these kind of local transformations, we end up in a situation that's a global transformation from the state that we started with. Okay, of course, we also evaluated this method. So this is from this year's iClear paper. And here we saw, so there's a little bit different type of graph. Now on the vertical axis, we have the wait time for the vehicle, which we want to be as low as possible. And we see that whether we take the standard message passing networks, it's a type of graph neural network, or we take a data augmentation based baseline, neither of those really do very well, and neither of those learn a lot actually in the time that we give it. However, the equivariant message passing network clearly does a lot better than any of the baselines. So that brings me to the end of this part. So these NDP homomorphic networks require fewer interactions needed in single and multi-agent settings. And this can be also applied in other works, such as we've seen papers on robotic grasping, representation learning, dynamics modeling. Of course, we also still have open questions, such as can we do something with approximate symmetries, so we don't hold completely, or here we assume that the symmetries were given, but what can we do, if they aren't given, can we identify them? So those are some interesting questions. That brings me to the second step of the plan for today. can we add ontological knowledge from publicly available data to provide an agent with knowledge about the world? This is joint work with Niklas Hupner, PhD student at the University of Amsterdam, and Ilaria Tiddy, who is at the Free University, the other university in Amsterdam. And this is based on an earlier presentation by Niklas of our accepted HCAI paper. So the core problem that we're focusing on is, right, if we're handling tasks that have, let's say, natural language or perhaps other formal descriptions, we might go into a lot of concepts that we hadn't seen before, right? So there's like, okay, we have to clean up a dirty plate and a red apple or something like this. Maybe our agent has never seen a red apple. So, okay, what can it do? Well, it could start to, let's say, randomly explore, right? And put the apple in the dishwasher or something like this. So there's many possible actions that it could take. There's many different objects and many different kind of actions that it could do with those objects. And that means that kind of trying to solve such task with trial and error requires a lot of exploration, because you have this large number of plausible actions. However, yeah, a lot of them are not nonsensical, like putting the apple in the dishwasher. And what we try to do here is, can we use knowledge that's already formalized and available, right? So not requiring too much engineering to help reduce the number of actions. So perhaps if we have from a public data set, we can extract the information like, well, apples are in fridges and plates are in dishwashers, then we can perhaps right, learn this task more efficiently. Now, earlier work, such as actually the work that uses at location property, did already do some work in this direction of using this common sense data from, for example, ConceptNet. And there, right, they kind of extracted kind of task relevant information by kind of manually extracting data or coming up with something quite task specific, or coming up with something that really relied on direct neighborhoods of concepts. And the question we ask ourselves here is, can we use this type of data in a more generic manner, right? Something that works across multiple tasks. So the property that we then ended up identifying is kind of abstraction. So in all of these data sets, you have instance of relationship, right? Like kind of banana is a kind of fruit, and a fruit is a kind of food, and so on. And our idea was, so grid concepts that are in the same branch, they are probably quite closely related, kind of regardless of which task you have, or at least in a relatively wide range of tasks. So probably apples are somehow closer to bananas in a lot of tasks, rather than apples being close to potatoes, for example. So we think we can use these relations to predict properties of objects that are unseen in the data. So if we have seen bananas in the data, but not apples, we could predict that maybe apples are sweet or something like this. And we expect that if we use those properties, we can improve generalization and data efficiency. So first, we need to extract this data from some open source data set, the hierarchy. And second of all, we then need to learn policies in a way that they use this hierarchy. So for the first step, right, we looked at the games or the reinforcement learning environments that we want to solve. We extract all of the entities that we have from it, like bananas, apples, and potatoes, and so on. And then we query all of the subclass relationships kind of recursively to build up this whole tree. And we can start with different online data sets. So we can use WordNet, we can use ConceptNet or DBpedia. We pre-processed this a little bit because we saw initially that we sometimes get this very unbalanced trees, so not kind of nice binary trees that are, let's say, balanced, but sometimes having concepts that have just a single child, so you kind of get this pathological formation. So we kind of collapse those layers down. And then the type of tree that we extract can look like this. The font size here might be a little bit small, so I don't know if you can really read it. But if you, for example, look at the topmost node here, it says cooking utensil, and then we have things there like pan, pot, kettle, and spatula. So that seems to work quite well. But I also want to point out that it's not completely perfect. So for example, towards the bottom right, you might see a node peeler. A peeler is, of course, right, kind of an ambiguous word. It can be a piece of kitchen equipment to peel potatoes, or it can be a person that peels potatoes. And probably in this setting, the first is meant, but it's here classified as a person. So, right, we get these trees that seem pretty decent, but not perfect. So also our subsequent learning algorithms should be, let's say, mindful of the fact that there could be, let's say, errors. Now we want to use these concept hierarchies to abstract away from the original states. So I want to give here kind of an example task of just kind of picking a meal. So I give you a range of food items and you can just pick whichever you find most attractive to eat, let's say. So I could say, okay, do you want an apple or a beetroot? But maybe our agent has never seen a beetroot before, or maybe our agent has never seen an apple before. So, right, then the agent presumably wouldn't know which one to choose. But in this case, we can use the hierarchy to make an abstraction. So we can make, right, one step of abstraction and just replace the concept by concepts one layer higher in the tree. So you can say, do you like a fruit or do you like a vegetable? Or you can abstract one level more and you say, do you want some plant-based food or do you want some other plant-based food? Now, right, depending on the situation, right, you might choose a different level in this tree. So there's some kind of trade-off where with the very concrete objects, the risk is higher that maybe you haven't seen one of them before, so you have no clue whether that's something you like or not. If you abstract a bit, you could do better overall. So for example, right, in general, I prefer fruit over vegetables, so let's go with the apple. But maybe I like fruit in general, but I absolutely hate apples, right? So there is some risk that you kind of lose some kind of precision. And then if we go further and we say, do you want plant-based food or plant-based food? Of course, I'm losing any information that I had. But that level could still be useful if I was choosing between apple and cheese. And I say, oh, do you want kind of animal sourced food or plant-based food, let's say. Because kind of in a situation-dependent manner, depending on the situation, we might choose a different level of abstraction. We don't want to kind of just go for one. We kind of want to combine the information somehow. So our first attempt was as follows. If we, for example, try to learn something like a Q value, so like how good is picking an apple out of the set apple and beetroot, then we could try to learn, for example, 3 kind of auxiliary, let's say, Q functions, like Q1, do we want to pick an apple out of apple and beetroot? But then also, do we want to pick a fruit out of fruit and vegetable? And do we want to pick plant-based out of plant-based and plant-based, right? We can define a loss on that and try to learn it. The problem is we can learn kind of different type of trees that lead to the same values overall. So if we look at the left tree, what Q value do I predict for picking a banana? Well, we start with +3 for plant-based food, and then +1 for fruit, and then +4 for banana. That's 8. And in the right-hand tree is a 0 + 0 + 8, right? So it's the same loss. These 2 trees will lead to the same loss. But the right-hand tree is kind of useless, right? So now if we get a pear and have the right-hand tree, I would say, oh, it's a fruit that's +0, but it is probably not very predictive of how much I actually like pears. So we have another approach that we call the residual approach, where we have a loss at each level. So at the highest possible level of abstraction, we just want to do as good as we can. And then every lower level of abstraction, we want to correct as much as possible the errors that are still remaining from the higher level. And this forces the best possible approximation to be learned at each level individually. So it forces this interpretation of a tree where, let's say, shared likes or dislikes are brought up as high as possible in the tree, which helps in generalizing to new concepts. We tried this on a toy environment, where essentially we just built up trees of, let's say, arbitrary choices where with a reward attached. And we see that if we then create a kind of toy setting, which has a perfect abstraction, so the parent preference is perfectly indicative of the children. Of course, it's very easy task to learn for all the methods. So red is a method where we don't use the hierarchy. Sum is the first method where we just sum up the auxiliary functions. And then blue is the residual method where we try to predict those residuals. But if we go to the test set where we have unseen objects, of course, if we don't use this hierarchy information, we will be unable to predict anything reasonable for unseen objects. So this base method just collapses. We can see what happens if we have ambiguous trees. So those are trees where sometimes you have nodes that have just a single child, and there it's unclear at which level you have to assign the credit. So the problem with the two different trees that we saw before. Here we see something a bit similar. All of the methods can learn in the train condition. In the test condition, the base method collapses. But here we also see that the sum method is struggling, right? So it's exactly because of the problem highlighted before. And then we can have noise. So sometimes there are exceptions where, okay, we like fruits overall, but some fruits we really hate or something like that. And here, we see that the oracle, which uses, let's say, the perfect abstraction that you could, cannot really take those exceptions into account in the train set, but it's actually good. It doesn't overfit to them. It works very well in the test set. But this relies on kind of manual knowledge of what the perfect level of abstraction is. So in reality, we would have to pick either the sum or the residual method. And we see again that the residual is more robust to this kind of noise. Now, this of course doesn't say so much, right? Because we assumed some useful knowledge in this hierarchy, and now we created toy data where there was useful knowledge in the hierarchy. So, okay, does this also actually pan out? We tried now seeing, okay, if we use these trees extracted from this publicly available data set, and then try those on a game, right? A game that's not connected to these data sets at all, but except that probably there is some semantic connection between the apple as used in the game and the apple as used in the data set. The first is the Text World Common Sense games. That's the game about kind of cleaning up dirty plates and apples in fridges and dishwashers. And we compared that to using pre-trained embeddings of all of these different concepts, right? So it's a different way to try to take into account like maybe apples and bananas from somehow similar embeddings. And located at triples encoded via graph attention. So if we look now at so these are the results after training, where in the middle column, you see the validation results. So those are unseen scenarios, but with known objects. And the third column is the test set. There we have unseen objects. We see that all of the baselines in the test conditions score under 90%. If we have, then we get the next two lines, the ones here labeled MR and MS. Those are the manually find, let's say, perfect abstraction. There we see we score very high. And then in the bottom row, we have the actual, right, the abstraction extracted from the public data set. And there we see that the sum method doesn't do so well because this tree is a little bit kind of noisy and redundant. But this residual method is actually able to mostly overcome that and score very close to what this perfect abstraction would do. So yeah, we found that quite encouraging. Then we also looked at another game, which is called Wordcraft. Here you get a set of objects and you can kind of combine objects, and then they will form different objects according to some rules. So you might have something like plant plus tree equals bush or something like this. And then you want to kind of create some kind of goal object. And again, we have unseen goal objects at test time. And here we looked both at, maybe I'll just start by the dark blue line in the bottom of the graph. That's if we don't use any abstraction with random embeddings. If we add to this random embeddings either the residual or the sum method, we get the red or the yellow line, which do a lot better, obviously. But again, we can also take the semantic information into account by using word embeddings. And here's these are the Glofi embeddings. So we see if we do that, we get the green line, which is actually even better than any of the things that we have. The best performance you get if we combine the Glofi embeddings with using the hierarchy information. So whether we use the residual or the sum method, we get to the top line in the graph here. Right. So so what we did was to use hierarchies from public ontology data, and that was helpful in solving these common sense games. And out of the two approaches that we designed, this residual approach was more robust to, especially to kind of, let's say, adverse conditions than the more naive sum approach. And overall, for the whole talk, right, I hope that I've been able to convey that using structure and prior knowledge are useful steps to improving data efficiency in learning agents. So that was what I wanted to talk about today. I want to thank you all for being here and for your attention. And of course, I'm more than happy to answer any questions you might have.
Thanks. Thanks a lot, Herke, for a great talk. Now there's some time for questions. So who has the first question?
Fernando, I have a question. Is right?
Yeah, go on, Francisco.
Hi, Herke. Thank you very much for your presentation. It was really interesting. I have a question regarding, well, when you mentioned in the traffic light problem that you showed, you mentioned that for the distributed task, you would need a sort of communication. But I was wondering if you have analyzed any further implication. For instance, I was thinking in real-time applications in which maybe not only communication can be an issue, but also maybe coordination between that. Oh,
I see. Yeah, I think we didn't study that in this work. That's the short answer. That's definitely something that is useful, right? So especially if you have kind of random policies, right, as we have here, you might say, okay, right, we maybe I could try to do this or that, right? The one agent could make a choice and the other agent could make a choice, and maybe both choices can be good depending on what the other does or doesn't do, right? So maybe you kind of want to take that into account when doing exploration. Yeah, I think that's a very valid point, but it was not what we focused on in this paper. Yeah.
No, I understand. I think it's also probably part of the future challenges as well. So I think it's interesting to discuss. I do have a follow-up question, sorry, about the other approach that you show when you rotate the image for this symmetric. I was wondering, the rotation that you introduced was always 90 degrees?
No, actually, so yeah, it only was. So in these two experiments, it was actually not a rotation; it was a flip. So this card pull is kind of flipping left and right.
Yeah, you're right. Yes,
you can flip top and bottom. In the traffic light example, it is multiples of 90 degrees. It's either 90, 280, or 270. We have all of them. That's it. Yeah.
So in that regard, the symmetric that you apply, it's problem related, no? I mean, it's not a common symmetric for all problems that you need to be associated to a particular problem.
So the good thing is it's often relatively intuitive, right? Whether if I rotate maybe a picture, it might not make sense, right, to have the sky at the bottom, let's say. Whereas if I have, let's say, maybe an MRI image, that's just like some tissue. Well, if there is some pathology there, right, maybe some, let's say, a tumor or something, if I rotate the slide, okay, it's still, the pathology is still there, right? So it's often, let's say, relatively intuitive whether there should be symmetries or not. But yeah, we do assume that we know for the problems which symmetries we can use. And that was also another future challenge to like, okay, can we also extract that automatically?
See, thanks, Helge.
I also actually have a question about this figure here. So for this particular domain, like the communication channels are also occur between adjacent agents, but I could imagine you could also have some diagonals. So basically the question is, how are there any scalability issues related with the connectivity, both the connectivity, but also the number of agents in these for the distributed case?
Yeah. I think computationally it scales quite well, right? Because essentially the number of messages sent is linear in the number of agents and linear in the number of neighbors per agent. When the number of neighbors wouldn't really grow if you make this timing bigger. The one question is, okay, if something can influence me from very far away, right? Then can I get the information from very far away? The way that we implement communication is through this type of, let's say, graph neural network or message passing network. So there can be multiple rounds of message passing, and in every round, the signal can propagate kind of to one neighbor more. So if we have enough rounds of message passing, eventually information could reach us from very far away. But yeah, we all know, let's say, from recurrent networks and so on, like this information doesn't travel perfectly, right? There's also information that's lost. So if you have the situation that you need to react to something that only someone very far away can see, then it would probably not scale perfectly. I think in this domain, typically, right, what's most important, what you do is really what happens at your neighbors. So I think in this traffic light domain, it would scale quite well, but we didn't actually test that.
Yeah, thanks. Are there any other questions? So in the meantime, and it's a bit specific, but in the previous work, when you were creating the equivariant layers, you had to initialize a lot of weights or just throw a lot of random weights. Do you have a sense of like what's the number of weights that you need, or at the distribution that you use initially, such as the uniform distribution?
Yeah, it's a bit of a while ago, so I hope I answered correctly, but I'll do the best that I can. I think we just used the Gaussian distribution. I think the number that you need, it's kind of related to how big this subspace is that you're trying to identify. Now, where is it?
Yeah.
Here, right? So kind of if you just try to find this linear subspace, then kind of 2 points would basically be enough to define that. But if you're looking, right, if you have 1 million of weights, you need a lot of points essentially, right? Even if you want to find kind of a smaller than million dimensional subspace, still it's probably going to be quite large. This is though, it's a kind of pre-processing step, right? So we need to do this once at the beginning. This doesn't depend on the data or on the learned weights. This only depends on the symmetry that, right, we assume we know it ahead of time. So we know the symmetry, we compute the linear subspace where we want to find the weights. And then we start training and we start looking at the data, but during the training process, we can only stay on the blue line. So maybe I didn't explain it very clearly, but so even if it takes a little bit of work up front, it's not something we have to do, for example, in every training step.
Hi, Herc. I have a short question. I'm curious about the application of this exploration of this structure of the problem in the offline setting. So this is a case where we usually have a limited amount of data. It's very clear. But then perhaps for some situations, we don't have enough data. And then if we can exploit this kind of structure, then we could generalize for these new situations. Have you explored that? Do you see what would be the challenges in this case?
Yeah. Okay. So we haven't explored the offline setting. I think you're right? I think one of the let's see. Let's take this picture, for example. So there's two, let's say, conceivable benefits, right? The one is if we have some data, for example, in a situation where the pendulum is falling to the right, and some data where the pendulum is falling to the left, but not that much, by kind of being able to realize that these two situations are related to each other, we can use data from both situations to improve each other as well, right? So you can kind of pool the data from all of those different situations. And the other possibility is, okay, maybe I have a lot of data for the one where it's falling to the right, but nothing where it's falling to the left. And then also you could kind of, you know, realize that you need to do a, the transformed action in that case. Theoretically, that shouldn't be any problem. I think in the, so right, there is, we look here at the specific case of kind of the state action symmetries. Of course, there's a much wider body on equivariant machine learning. And I think they have done this kind of experiments okay, what if we now introduce some situations that we haven't trained on before, but we didn't look at that exact problem in this work. Yeah.
Thanks.
But I would assume that it would work. It sounds very possible. Yeah.
Very likely. Yeah.
Thanks for the question.
Any other questions? Just hit the hour. So we'll create a Slack channel. So if people ask questions about your talk and to discuss, we can do it there, and then I can forward you any questions or comments. But if there are no more questions for now, yeah, let us thank you again, Erke, for accepting our invite, and thanks a lot for the talk.
Thanks for the invite, and thanks everyone for your attention.
And we'll have a short break until well, in 15 minutes. I don't want to risk and say hours in different time zones. People are spread all over the world, so we will meet again in about 12 minutes for Bay's talk. So please hold still or show up in 12 minutes, and see you later.
Bye-bye.